Hello, my name is Bill Buchanan, and I lead a podcast on the world leaders in cryptography. And today I have a true world leader, Giuseppe Ateniese. Hi, Giuseppe.
Hi, Bill.
So, Giuseppe is a professor, Eminent Scholar in the Cybersecurity and CCI Faculty Fellow in the Department of Computer Science and the Department of Cybersecurity Engineering at George Mason University. He has advanced many areas of research, including proxy re-encryption, anonymous communication, two-party computation, secure storage, and provable data possession. His current work includes privacy-preserving machine learning and distributed secure computing based on blockchain technology. He received the NSF CAREER Award for his research on privacy and security, and the Google Faculty Research Award, the IBM Faculty Award, and the IEEE CISTC Technical Recognition Award for his research on cloud security. Giuseppe was a researcher at IBM Zurich and a scientist at the Information Sciences Institute at the University of Southern California, and worked briefly as a visiting professor at Microsoft in Redmond. He is a Farber Endowed Chair in Computer Science and Department Chair at Stevenson's Institute of Technology. He previously worked at the Sapienza University of Rome. Hopefully, I've got that right. You can correct me if I was
Sapienza.
wrong.
Yep.
Okay, and was an associate professor at Johns Hopkins University. Giuseppe is also one of the JHU Information Science Security Institute's founders. So, Giuseppe, what's your current role and what does a typical day involve for you?
Thanks, Bill, for this interview. So, as you said, I'm a professor at George Mason University. Most of my day is basically research with a smaller slice of teaching.
Mm.
Right now, basically, big part of my day is learning. As you know, my home base is cryptography and security, but I'm also investing time in learning about machine learning because I think it's now part of the security story. So basically, I spend time with colleagues and students trying to spot good problems early. And we also run reading groups where we look at problems at the intersection between machine learning and security. We try to understand, what is real and what is hype. And then we pick one or two directions and we go deep in those.
Do you worry about agentic AI?
Oh, yeah. Yeah. I mean, I think it's we look at this topic in recent years, and yeah, I think the intersection between security and AI is very important, and agentic AI is definitely one issue that we are looking into right now.
Yeah. It's quite a scary world when you think about it, that these agents will have our passwords, our cryptography keys, can run
Indeed,
wild. And I think if we don't, if we need to watch that, we need to lay a foundation of cryptography to make sure that agents can communicate with each other and trust each other and also have linkages to the person too. So maybe we can talk a little bit about that later on in the podcast. So going back to the past, how did you get into cryptography?
oh, well, I did my master degree in the University of Salerno in southern Italy, and there I met my advisor, my thesis advisor, my master thesis advisor, Alfredo De Santis, who was like a cryptographer, and he's a cryptographer. And he built in Salerno a top-tier research group at the time, and he worked on many interesting cryptographic problems. So for my master thesis, he gave me a paper to read that was like visual cryptography by Naor and Shamir. And the task I had was to basically digest this paper. So it was a very difficult paper, particularly for a master's student. So, but I think after like 1 month or so, I started loving this paper. I started really understanding this paper, and I actually came up with a completely new solution for it. And we extended that paper, and my master thesis actually resulted into I think about like 3 or 4 research papers published in top tier conferences and journals. So
from your master's thesis.
From my master thesis, yes, that was an incredible.
Like Ralph Merkel, perhaps he published many papers while he was an undergraduate.
Okay, so I'm not at that level for sure, but yeah, it was an impressive work we did, and Alfredo taught me to basically look at these problems from a very analytical point of view. He's very analytical when he look at problems, more like a chess grandmaster. You know, he thinks about it and goes really underneath the structure of these problems. So, and so we were able to work on visual cryptography, and from there on, I think I fell in love with cryptography, and I continue working on this.
That's great. So what topics do you currently teach? And what's your favorite ones?
Well, of course, the obvious answer is cryptography. I teach cryptography at least 1 semester per year. And but honestly, when I teach, I like to also learn. So I currently also teach algorithms, which allows me to, explore topics like they are tangent to cryptography, like, I don't know, NP completeness and complexity theory in general. So I like to teach possibly topics where I need to kind of learn a little bit more. So I do it also for myself, not just for the students. So yeah, I'm teaching crypto mostly and algorithms. I hope to teach something connected to machine learning and security in the future. And sometimes I also teach a class that is related to blockchain technology. Yeah, so because students, particularly undergrad students, are really interested in this technology. So we have a class in blockchain. It's not like part of the curriculum yet, but we teach occasionally also this class. Yeah.
Yeah. And for your maths, were you taught the mathematics that you use in cryptography in your courses that you took, or did you have to learn all of these new methods in cryptography like finite fields and discrete logs yourself?
Mostly myself, I have to say, because once I became interested in cryptography, I kind of had to teach myself about number theory and complexity theory and so on and so forth. I wasn't like a great student early on, so I didn't have much of the math background that you would expect from someone working in cryptography, but I learned most of my math background during the university, so at the undergrad and graduate level. But I didn't have like a very strong background in mathematics at the beginning. during, say, middle or high school.
Yeah. And the visual cryptography paper by Shamir was what year was that? When was that published?
In the 90s, late
90s.
90s,
Yeah.
something like 96 or 7.
Yeah. So what other things were happening around that time? So we were obviously past the Diffie-Hellman RSA. Shamir did a lot of great work in the 1980s. What was happening in the 1990s that you remember, apart from the visual cryptography?
Well, there were many discussions also about payment systems, I remember, like precursors of the blockchain, right? So I
Vivichal.
remember many projects of Bitcoin, I would say.
Yeah.
There were many work, particularly in Europe, about payment systems. I remember a lot of works in smart card security, smart card payments, anonymous payment systems. That was like a very interesting area that actually I focused on. And I don't think I ever published anything in that area, but I remember studying it, this topic. And indeed, when Bitcoin came up later, honestly, I think it wasn't that surprising to a lot of people working already in this kind of projects. So it was kind of some sort of a natural extension or of the work that was happening at that time, particularly in Europe again. Even a lot of universities were using systems in the 90s, like exchanging coins through wallets, private
Oh,
wallets. Yeah,
okay.
they were protected by smart cards. So it was mostly they were mostly based on hardware security rather than, of course, something like the blockchain or a decentralized uh, storage system. But yeah, I think that area was happening at the same time.
Yeah. You obviously had the crypto anarchist agenda going on at the time.
Yeah.
Sort of Timothy May and so on. They were setting the landscape for Satoshi Nakamoto to come along and actually create Bitcoin. So, so what's your current focus on research at the current time?
So I'm mostly working on machine learning and security. So the combination of the two. Of course, when I say security, I really mean cryptography in a sense. So, for instance, I've been working on watermarking, with which requires some knowledge about cryptography and as you know, we use LLMs every day, but we want to basically understand whether something is coming from a generative AI system or not. And so companies are discussing now the possibility of watermarking this output. And for instance, Google uses a watermarking scheme for the Gemini family of models. So I was intrigued by these techniques. Of course, watermarking is not new. I mean, has been studied for a long time in cryptography and security, but watermarking the output of generative model is new and some interesting nuances. Um, anyway, what we basically proved in our papers is that watermarking in a strong sense is basically impossible, which is kind of surprising in a sense, because if you think about it, both Europe and US are kind of mandating through legislation that the output of generative AI has to be kind of watermarked, and you think that then this is technically feasible, but you assume that they did the homework, and they learned that this is actually something feasible. But in reality, we show that it's impossible under certain assumptions. So we had a paper recently where we showed that through some mathematical techniques called random walks, and assuming certain oracles, like a quality oracles and a perturbation oracle, that you cannot really watermark the output. Yeah, just to give you an example, since I'm Italian, I can give you an example with, say, an espresso. I like to give this example when I talk about this topic. Imagine you have a coffee, like an espresso, and that's the output of a model, say, ChatGPT. You want to watermark it. So what you do is you add some cream on top, and this mark is basically what tells you, okay, this was generated by generative AI. So the hope that the designer of the watermark have is that this mark, this cream, even if you stir it, will still stay, will be there forever. So, or if you can remove it by stirring, the hope is that you have to stir an insanely amount of time, like billions of times. What we show is that no, first of all, if you stir it, you can remove the watermark. So the cream will basically disappear. So you will just see, black coffee. And the amount of stirring is actually limited. In most of the schemes that we analyze, you have to stir like, say, 30 times. So it's finite, and it's a very small number. So basically, there is no hope if you want to watermark content to prevent attacks like misinformation, say, from very powerful adversary. This doesn't mean that watermark is completely useless. I mean, watermark has still use cases. Like if you assume that the adversary has limited power and doesn't spend too much time rewriting or changing the content, massaging the content, or make perturbations to this content for too long, then you can still have some mark that will resist this kind of attacks.
So I understand how images, video, and sound could be watermarked. So we can put cryptographic methods in there. We can put a key in, and so on. We can put in noise that will stay in there. But when it comes to text, like with ChatGPT, from the methods I've seen, it's having some way to maybe embed a cryptographic key into the words. So when you know the mask, then you can apply the mask, and the mask will actually show you. And it still makes sense as far as I can tell. So the grammar is still correct, but the words are certainly placed, or the full stop is in a certain place. And as you say, if someone doesn't stir the cream or the coffee, it still stays. Is that right? Is that the type of watermark that you have in text? Is it a matter of arranging the words and using certain words?
Yeah, I mean, there are basically, in general, for watermarking text, there are basically two, I would say, main techniques. One is called like, say, green, red list, meaning if you think about it, ChatGPT is nothing else than some sort of prediction mechanisms of the next word on steroid. right? So,
Yeah.
so what ChatGPT does in the end, when it has to generate text, it's going to have like a list of words that could be the next possible word in your text, and it will make a selection of this word, of the next word. So imagine now you have like instead of having a single list, you have two lists, like green words and red words. They're both okay. If you pick any word in these two lists, you will be fine. Your text will look like legitimate text, high quality text too. But imagine now the model will pick always from the green list instead of the red. So even if both are fine, it will constantly pick from the green list. And so in the end, your text is going to look fine, high quality, but it's going to be picked from the green list rather than the red list. And this is how you watermark. So if you don't know as user which one is the green or the red list, you have no idea that your text has been watermarked. But if you know the secret that allows you to distinguish between green and red, clearly when you see a text, you see that it's coming mostly from the green list. So you know that this text is coming from say ChatGPT or a generative AI model. So that's how they do it. These were like the first watermarking techniques. What I like more though is a more cryptographic approach to this problem. And there is very recent work on what are called pseudorandom codes. If you know how these models work, like LLMs, they do all this next prediction process, but they start from some sort of pseudorandom number or random number to start with. Indeed, when you do some prompt to this model, even if you give the same prompt, you will always get different responses because internally these models use some randomness. Now imagine you can tap into this randomness, and instead of using a real random number or a pseudo random number, you use some special code, which will influence the way the model will output the text. So now the model behaves exactly as before because it starts from what believes to be a pseudo-random number, but in reality this is a specially crafted code that will influence the behavior of the model. It will end up outputting something with some distribution that you can detect. So this area is very interesting in cryptography because it allows you to make a watermark which is essentially undetectable, meaning this code is so specially crafted that is indistinguishable from random. So if you were able to distinguish that there is a watermark in your text, you would basically have a method to distinguish between random from pseudo-random. So you will break some cryptographic assumption. So which we know it's extremely difficult. So there is this other area which is more like cryptographic based for watermark, which I really like. And by the way, our method of proving the impossibility works also for this new type of cryptographic watermark. Unfortunately, if you allow our adversary will always be able to remove even this type of cryptographic watermark. So again, our method works for independent of the watermarking scheme.
Yeah, there was some interesting work that was looking at words that have appeared in conference papers in the last few years. I think some research looked at PubMed and the word delve had hardly been used at all. And then all of a sudden it increased massively. And they came up with, the paper I read came up with about 20 words that we would never actually use typically in English and in academic work. And then all of these words. And one thing that was posed was that an LLM training goes through the neural network part of the training, and then it goes through the human part. And it was reckoned that the training with humans was done in another part of the world, possibly where there was cheap labor. And in that area, the word delve was actually quite popular. So it
Yes.
was actually selected. So this has brought all these words, and certainly myself, I can spot Gen AI a mile away. If it hasn't been edited, it just looks wrong, especially if it's a student coursework. It's off topic, it goes into detail and so on. So I think there are still some human ways that we can still detect. The citations, it still struggles. I got one coursework. Citations all looked fine. It was Shamir and Revest and so on. But when you looked at the citation, it was actually wrong. It was the wrong journal. It was the wrong year it was published and so on. So there are still gaps there. Do you worry from an academic point of view about your students using Gen AI? And how could we use these watermarking techniques to maybe help students stop them from just copying?
Before I answer this question, I wanted to add that detecting text from Gen AI using this kind of techniques, though, it's kind of controversial. I don't think they work, and we should probably stop using them because models are getting better and better, of course, in generating text. And also, if you know how to prompt the model, you can avoid this kind of detection. And so it has been shown that these techniques do not actually work. So you may use them and falsely accuse people of using generative AI. So one has to be very careful. So I'm completely against using this kind of techniques that are not really based on, foundational cryptographic type of notions. Indeed, this comes to your next question. How can we detect students using AI and so on and so forth? Personally, my view is that students should use AI. I encourage my students to use AI because my problem is that if students don't know how to use AI, I think they will be completely out of this market, the future market. So it's important to use it properly, of course. They should use them, this generative AI as tools, not to find shortcuts into the learning process. But so what I do for instance, in my courses, I encourage students to use AI, and as part of the learning process. Like we use, say, the web, the search. We'll use Wikipedia, or we use, say, Google or calculators or computers to help with our work. The important thing is to understand whether this is part of the learning process, which is fantastic, as a tool, or whether students are trying to cheat and use these outputs instead of their own work. That's still open to debate. I don't think we know exactly what to do. Personally, I think we should go back to doing exams in the old way, like oral exams, in-person exams. That's probably the only way to really determine whether a student is prepared. The way it's done now, particularly in the US, where you give a lot of homeworks, may not work in the long term. But I will never discourage a student from using AI. I think actually I'm doing the opposite. I'm trying to give them it's very difficult. For instance, this semester, what I did was to encourage them to use AI, and I gave them like very, very difficult problems. Problems where by yourself, you will never probably be able to solve it. But in combination with AI, you have a very good chance of solving it correctly. But you have to be at the same time really prepared, because using just AI will not allow you to solve that problem. Because AI, of course, as you know, will hallucinate or will give you some answer that is not the right one. So you have to be an expert in selecting the right answer, or steer the model into something that makes sense for the specific problem. So I tried that. It seems to work, but the problem is that these models are getting better and better and coming up with difficult problems where you need the combination of human and AI is going to be very difficult. So I don't think I will be able to do it for a long time. So I think we will have to address this more at the fundamental level, like again, as I mentioned, like doing probably in-person exams more often.
Yeah, I agree. And obviously, every time we prompt our Gen AI, it's actually learning from our prompts and it's reinforcing something if it gets the right answer. So if a student puts in a prompt related to, we would call it courseworks, as you would say, then it will actually try to learn from that. And then the next student who will ask, it probably has a better answer than it had before. And it's obviously trying to answer, Google is trying to answer every question that could ever be, just like Stack Overflow we used to use at one time. It's trying to answer every question that is actually possible. So, so what was your contribution with the paper on provable
Probable
possession
data possession, yes.
of untrusted data stores?
Yeah, so that was a while ago. So basically, we at that time, cloud computing or cloud storage was the main topic of discussion of research. And by the way, indeed, at that time, everybody was mentioning, oh, cloud storage or cloud computing was really bad from a company perspective, because we had to give these companies providing cloud services or our data and so on and so forth. So there were discussions like we have discussions now about AI, but as you know, now everybody is using cloud storage or cloud computing anyway. So all those problems were kind of resolved. Anyway, the problem was, okay, so suppose we want to use a cloud storage provider and we want to store our database, which is very big. It could be terabytes of data. We store there. Of course, we delete our local copy, because the whole point of using cloud storage is to rely on that kind of storage remotely. We don't have a local copy anymore. So the question becomes, how can we be sure that the cloud provider is storing everything intact? Every single bit, possibly, or at least the majority of it. So the trivial solution would be, okay, so maybe once every week, I will download the entire database. I would probably store some kind of hash of the database or some message authentication code or whatever. And I download the whole thing and I verify that the hash is still correct. This solution, of course, doesn't work because I will have to download the entire database. So another possibility would be, suppose this database is stored in blocks. I can basically challenge the cloud provider and say, give me block 1, give me block 10, give me block 100, give me block 1000. And pick these blocks randomly and unpredictably, and then verify that the hashes of these blocks, which I stored locally, will verify. Even that is not really acceptable to me, because if you think about it, I would have to download all these blocks anyway. This consumes bandwidth, and also if you want to really have assurance that your entire database is mostly intact, you will have to challenge on many blocks. So what we did with PDP, or provable data possession, was basically to come up with an idea where we don't have to download anything. Why downloading the blocks in the first place? Why don't we ask the cloud provider to do the heavy lifting work? So we asked the cloud, we came up with techniques called homomorphic tags, some sort of, think of them as message authentication codes that can be combined homomorphically. So we ask the cloud provider to basically read the actual books I'm challenging the cloud provider on, compute the tags on these books, and combine them into a very short, condensed message. And just send me this message, which is very short. It could be like a few hundred bytes. And this is basically a proof that all the blocks I've challenged you on are still there intact. If a single bit of any block that I challenged you on is changed, this kind of condensed proof will be completely broken. So this was kind of a very interesting and novel technique at that time, because you basically now you can verify that the cloud storage stores like terabytes of data, and but you just verify a very short proof. So you don't have to download anything. You don't have to have a local copy of your data, and it kind of sound even counterintuitive if you think about it. How can I verify something without even have an idea what this something is supposed to be? So that was a very interesting work, and there was a lot of. We opened basically an entire area on provable storage in some sense, and after that there were so many interesting innovations. Our schemes worked with a database that was kind of static. But the reality is that people change these databases. How do we adapt the schemes where the database can grow or shrink, or files can be modified, and things like that. So I hope I answered your question.
Yeah, yeah. And I know there's a lot of work in proof of storage and blockchain methods. So like a proof of work rather than consuming lots of energy, you can do a proof of storage where you need to download all of the data to then be able to prove, as you said, you can randomly pick a block
Yes.
and you can't cheat. You've got to make sure that you, and it sounds like the method you proposed is the kind of similar type of thing. There's no way I can cheat. If I don't have your whole database there and I have the 1 petabyte of data that I'm reserving, then you can't actually cheat. And it's interesting you say homomorphic encryption, and obviously that's going to be the holy grail for a lot of these applications. We're not quite there in terms of the computation and the requirement for GPUs, but I think the next 5 years should start to see a lot of our cryptographic primitives, like pairing-based cryptography, moving towards homomorphic encrypted methods. And it'll be good because they'll be post-quantum robust, which is good, but it's a whole lot of learning from elliptic curves into lattices is a big jump. I don't know how I'm going to teach lattices because I teach elliptic curves and RSA, which is fine, but to teach lattice might be a little bit more difficult. So a great fan of proxy re-encryption overall. It maybe is still trying to find strong use cases. Some people are quite critical of proxy re-encryption. Could you explain basically what proxy re-encryption is all about and what you think is the best use cases?
Yes. So in proxy encryption, that's a different topic. We looked mostly at access control. So imagine I'm working with you on a Word document. It's encrypted under my public key, and I want basically I want to give you access to this document. The obvious thing to do for, say, a centralized cloud provider would be uh, to basically either I give you my key, and so you can decrypt, under my secret key, and you can read the document, or I can ask the cloud provider to decrypt it so I send a copy that is decrypted, and then we'll re-encrypt that document under your public key, so you will be able to work on this document. You can imagine that this kind of naive solution doesn't really work, because either I will have to share my secret key with you, which is not necessarily a good thing, and or the cloud provider would see the text in the clear, and before re-encrypting that for you, so that you can work. So we will have to trust this kind of proxy. So in proxy encryption, instead, what you can do is you can basically translate between ciphertexts. You have ciphertexts, say, for user A, you can translate them into ciphertexts for user B. And the nice thing is that this translation, you don't have to know any secret key at all. You can just translate it using what is called a proxy key. So whoever does the translation doesn't even see the plain text. So I can basically transform an encryption for A into an encryption for B, and I don't have to know any secret key. I don't have to see the message underneath. So it's perfect. And this enables, in my opinion, a lot of interesting application in access control, where whoever has to provide access to data is not necessarily trusted. Or even if it's trusted, that was, I think, your question is, some people find this not so applicable, because most of the time in this cloud setting, you trust the cloud. So when you do this conversion, this translation, you don't care too much about the level of trust you have with these providers, which is true. I understand that. I appreciate this point. But the point I want to make, though, is that these cloud providers are not necessarily secure. It's not the question I don't trust them. The question is that they could be compromised, and it happens all the time. If you are compromised, these keys will be released, and whatever trust you gave to this cloud provider is basically lost. So if you use proxy encryption, the nice thing is that even if an adversary or hacker compromises your system, they will only have proxy keys. So they will be able to do translation between ciphertext A and ciphertext B, but they will never learn the plain text. So in my opinion, there are a lot of interesting applications. And over the years, I've seen proxy encryption actually used in many academic environments, though. Hopefully, there will be more industry applications. But to me, the point that it's still missing is to understand that it's not really a lack of trust in the proxy or the cloud provider. It's more like whether this proxy or cloud provider could be hacked. And proxy encryption in that sense will really provide a level of security, because now you don't store any keys. You just store proxy keys, which just allow you to translate.
Yeah. One application I saw was an NFT sales. So let's say A is selling in a marketplace and the market provider is provided with A's translation key. So they're trusted enough so that when the buyer comes along, then it is then possible to translate A's private key into B's public key, which means that the NFT can now be decrypted by B's private key. So almost like you do have to have that little bit of trust in the
Yeah.
marketplace. But if it's an encrypted image, let's say it's an image that Alice has painted, she could encrypt that image, provide the translation key. Bob goes to the market, really wants to buy uh, Alice's art. Then we can then translate. He gives his public key. We then do that translation with the keys, and now he can decrypt with his private key. And the marketplace doesn't have the opportunity really to decrypt, as you say, in between. So there are use cases, but it's still not as strong, perhaps, as it could be. And I think it's important that we maybe investigate a few other use cases.
Yeah, I agree. I mean, yeah. I mean, I've seen also recent work by my PhD advisor, Jin
Mm.
Sudik, on how to use proxy encryption for um, uh, dealing with data brokers and so on and so forth. So, yeah, I think there would be more practical applications soon.
Yeah. In areas, and you applied this into identity-based encryption too, but obviously we see the rise of digital identity. I think in the EU, or it's mandated for EID and EIDAS2, where you'll have some certainty around digital signing in the future. And as far as I can tell, the European system will be using a blockchain to be able to store public keys, such as with Hyperledger. Uh, so how do you see these types of blockchains evolving? Ones that might give an anchor to digital identity. In the UK, we're discussing the possibility that we might actually have digital identity. We tried it in 2001 and it didn't happen. And it's a really difficult topic because people really worry about privacy. We saw the green passport around COVID time, and that worked really well. We could move across borders where we could have a public key signing system. So, how do you see blockchains evolving in terms of digital identity?
Oh, I think it's essential. Actually, I look at digital identity recently, and it's a very important topic. And I don't think it can work without a blockchain. As you know, the European legislation doesn't necessarily, or specification doesn't necessarily specify a blockchain as a storage medium. It could be even a centralized database. But honestly, if you look at the details, then I don't fully understand how this can work without the blockchain per se. And my understanding is that there is a blockchain, a European blockchain, which is permissioned
IPSI.
for yeah, exactly, for
Yeah.
this purpose. But I hope that they will adopt a more open blockchain like Ethereum that already has this type of identity mechanisms built in. Um, I think it's very important, and it's going to be mandated next year, if I understand correctly,
Yeah.
right? So
Yeah.
which it's a bit scary if you think about it, because I think of the average person to, I mean, they are supposed to basically use a wallet to store this keys connected to their digital identities. This wallet are basically very similar to cryptocurrency wallets, if you think about it. Actually, some of the technology is pretty much the same, at least for some. more esoteric cryptocurrency. They also use zero knowledge or proofs, and so the technology is not that different. Which makes me a little bit worried because, as you know, cryptographic wallets are basically used arguably by expert right now, right? So only really people into cryptocurrency that they understand everything will download a cryptographic wallet for off-chain storage of the keys or and still you hear about billions of dollars of money that is lost every year because someone compromises the keys or someone didn't back up the keys properly or something else, right? So I'm a little bit worried where you tell people then to store these keys somehow in a wallet, and what happens if the device is compromised? What happens if I lose my device and I didn't do the proper backup? I think in the US the story is slightly different. I think there is no from the last time I checked, there is no like a federal regulation or federal specification on this, but it's mostly based on two companies like Google and Apple. So Google and Apple basically have released some specification for digital identities, and they rely mostly on a secure enclave on phones. So the keys will be stored basically in a secure enclave in the phone. And I think they are actively working on how to then allow users to prove statements about their identity, how to do verifiable credentials, and so on and so forth. Although, again, even there, I'm not sure exactly how, for instance, this will protect the keys for sure. But I'm not sure how backup systems are going to work. What happens if I lose my phones, my devices? And again, this is connected to identity. I mean, if you think about it, in 10 years, everything will work through these keys, right? So how do we manage these keys is still not clear to me. Everything will be connected from our identities, our credentials, our money, bank accounts, cryptocurrencies, assets, tokenization. You know, it's the future of blockchain. So how is this gonna be handled? It's not clear to me. I think there is a lot of space here for research and coming up with innovative solutions that are closer to the real need. I mean, again, how do we manage these keys is going to be like incredibly difficult. So I'm very excited about digital identities, of course, as a cryptographer, but I hope we're not going too fast, assuming that the average user can manage these keys properly. Or unless we rely on custodians, which is another thing that the European specification considers, which is kind of also not very satisfiable, because now I have to give my keys to some sort of custodian, and how do I know that this custodian is working properly? We have seen this also in cryptocurrencies, right? So of course I can use like a online broker that handles my keys, but these brokers are sometimes hacked, and I lose my keys. I don't have control of my keys. Privacy is another issue. So again, it's all a little bit up in the air for my taste, but it's definitely exciting. As a researcher, I hope we can help this kind of field.
Yeah. I mean, it's probably going to be some sort of PKI type infrastructure for for a federated infrastructure where each country will look after their own blockchain with their own public keys for their own businesses, and they'll have to have some way of registering businesses onto it, like universities, if they're providing academic qualifications, then they'll sign the qualification with a private key, and then there'll be a public key which is on the ledger within inside that country. Other countries will trust each other, other public keys, just like PKI, but at least it's on a blockchain somewhere, so you can easily revoke. So there's lots of learning. I think Estonia has been really at the forefront of a lot of this type of thing, and they've got lots of experience of running digital identity systems. So hopefully the learning from a small country like Estonia can be used to scale across the EU. Hopefully the UK will be integrating in with that infrastructure, because it's a nightmare to develop your own digital ID system that isn't compatible with someone else's. I think the COVID passport showed that countries can work together very, very much.
Sure, yeah,
Overall.
that part will definitely work. Yeah.
And Ethereum is really the ledger of choice at the current time. It's really taken off so much, but we have this bottleneck that it can only cope with 10 to 20 transactions per second. So it's really going to struggle to scale up. But we've seen so much going on at layer 2 now, in that we're getting this multiplication, this off-chain activity, all the things that was meant to happen in layer 1, like these creating islands of activity, just hasn't quite happened. So it looks like much of the activity, especially in finance and so on, and crypto tokens, stable tokens and so on, is happening at this layer 2, around things like Zk rollups and so on. So where do you see Ethereum evolving? Do you think it is going to be the ledger of choice? Do you think our whole finance industry will be built around Ethereum, or are there other opportunities for blockchains to come along?
That's an interesting question. I would say, by the way, remember when I said that when Bitcoin came up, people, I think, working in the payment systems were not, I would say, shocked. I mean, they were surprised because, a system like that works and scales for millions of users was kind of surprising, but not like shocked. But honestly, when Ethereum came up into the scenes, that was shocking. Honestly, to me, it was like technology from, I don't know, some alien species or something, right? Because imagine you can do computation in a distributed way. I don't think anyone was thinking about it at that time. It was completely out of the blue. Like it wasn't even in papers or discussed in conferences or anything like that, if I remember correctly. Maybe I'm wrong, but at least when I look at Ethereum, I was like, wow, this is not something I've seen before. Or at least people were even discussing about it. Nothing was on the scene. So I'm not worried that Ethereum is slow, to be honest, because it's developing in a way that is secure and allows a completely new, as you said, a second layer to develop and thrive and solving specific issues depending on the application. So that's I don't think is a problem. And also in this field, you can always evolve. If there is another blockchain that does something better than you can always change your protocol and adapt and adopt the same technology. So I don't think Ethereum is slow by constriction or anything. It's slow by design and allows to the second layer to thrive. Whether it's going to be the blockchain of choice, well, that's still debatable, as you know. I think Wall Street in the US basically kind of decided that Ethereum is going to be the next one. As you know, there are like in the market, in the stock market, there are like treasury companies that are investing in Ethereum. They are basically buying Ethereum and sell shares to users. I think the majority of Wall Street players think that Ethereum will be the one selected. I cannot say, of course. I'm not that visionary, but it makes sense to me, though, because it's the oldest blockchain in this respect. Is the most neutral and trusted, in a sense. And again, there are other better blockchain, but better it's really relative to exactly the kind of application you want. And in this field, it's not like protected by patents or anything like that. You can always evolve. If you need speed, you can adopt the same technology or techniques that faster blockchains adopt easily. You do a fork and you change the underlying code of the blockchain and you adapt it. But again, I don't think this is a problem for slower blockchains like Ethereum. It's probably a design choice to be more reliable and secure, and allow also the second layer to thrive. Very much like think about app stores like Apple or Google stores, right? Where you have this market of applications thriving that do better than the underlying open systems. And you don't want to stop these applications from thriving, because you are actually gaining something from them, right? And you don't want to necessarily adopt all this technology that these new apps come up with and embed them in your operating systems. You just let them thrive and create a business out of it. And I think this is what Ethereum is doing. Again, I may be wrong, but this is my sense. So whether this is going to be the future, personally, I think so. But in Wall Street, I think the majority of people think so. And I think Wall Street has a view that stable coins will be the next important moment for blockchains. I think we don't have yet the ChatGPT moment for blockchain. To be honest with you, I don't think stablecoin is the ChatGPT moment right now of blockchain. Personally, I'm very excited about tokenization. So to me, that's the bigger long-term story. So where we can tokenize real assets like houses and cars, and that's where the big moment of blockchain will be. And once people realize that we can tokenize real assets, think of the beauty of the future, where now I can use my assets as I use stocks today in a market. So if I have a house and it's tokenized, I can protect my assets. I can say, if the price goes below a certain amount because of some natural disaster or something, I can sell it through a liquid market offered by the stock market. Or maybe I can run something more sophisticated, like options, and basically have insurance on my assets if they go down a certain level, or if they go up. I can instead of selling, I can try to monetize on that through what are called option call contracts. So to me, that's the next thing, right? So where users will be able to tokenize their assets and use these assets in a way that we use today techniques for stocks or for contracts, for futures and things like that.
Yeah. And the UK is just passing, has just passed a bill on digital assets,
Oh,
which really covers cryptocurrency, tokenization, and so on. In Scotland, too, we're passing a bill on that, and it gives legal certainty. It's almost been, it's there's no legal certainty. I know that some countries like Liechtenstein have created the Blockchain Act, but now I think bigger countries are catching up and knowing the opportunity to attract business to their region of the world. But there needs to be legal certainty, the protection of citizens, but
exactly.
also to be able to create the innovation that's required. So it's taken a while, it's taken decades for the legal industry to catch up, but I think it's getting there. It's a difficult thing to get right. So you've worked in many places. You've worked in industry, you've worked in academia. Which place did you learn the most from?
Oh, I learned from all places, of course. Whatever experience you do, I mean, you learn from that experience. I learned different things. Definitely, academia is my place for sure because of the freedom that gives you. I like to work on problems that I feel are more important or that I enjoy more. But I learned from all places. I've been to many academic institutions, and I learned from all of them, mostly through interacting with students and colleagues, of course. But also I learned a lot from leadership roles. I was a department chair at Stevens Institute of Technology in New York, and I really enjoyed that too. I mean, I like to have. I noticed that we do research. We kind of close ourselves into a room and think. But when you are forced to have a vision and lead an institution or a department, it's a completely different game, and I enjoyed that part too. So I learned how to have leadership kind of skills and manage people, which is very difficult, and have a vision. So yeah, I think every place gave me something extremely important.
Yeah. And you started off with visual cryptography. Could you just give us a simple sort of explanation of what visual cryptography actually is?
Oh, sure. This was a very cool concept by Naori Shamir. They were thinking, in my opinion, what can you do if you don't have computers anymore to decrypt stuff? I mean, right now we think, oh, if you encrypt some information, you can decrypt it using computers. But what if we don't have computers? What if someone destroys everything and you have nothing at the time of decryption? So what they came up with was a scheme where you can encrypt images, so basically everything, because you can embed the message, of course, in an image. And you can create, say, transparent slides, and you can print something on these slides. If you look at the single slides, you get nothing. It's information theoretic secure. You basically see like a very noisy image. Actually, yeah, I have it. So think about something like this.
Yeah.
So you don't see anything. So what if you stack them together? That's how you decrypt. So if you stack them together, you get the actual secret. So what visual cryptography allows you to basically create this slides and create like a threshold. You can say if say 5 out of 10 people stack together their slides, they will be able to see the secret image. If fewer than 5, they won't be able to do anything else. They will not be able to learn the secret. And this is an information theoretic, meaning there is nothing you can do. I mean, it's not even based on some computational assumption. And in my work in Salerno, what we did was to basically improve these constructions, but also extend it to a general access structure. So the original scheme worked for thresholds, say 2 out of 5, 5 out of 10, and so on and so forth. But in reality, what you want is to actually be able to say, oh, I want person A and B together to see the message, or B along with C and D. So you don't have to have a necessarily threshold. You want to have some sort of a general structure of people that can read the message. So you can list the sets of people that can read this kind of message. And this was kind of open, so we solved it in this paper. In other papers, we also generalized visual cryptography, because now in visual crypto, what you see is kind of a scrambled image. If you just look at a single slide, but what if you can see some image already? So it's kind of imagine you see an image of a tree and an image of a house, and you see them clearly. But then if you stack them together, this tree and the house disappear, and you see an actual secret. So that's what we call the extended visual cryptography schemes, where we can actually we don't need necessarily random noise on the slides, but we can actually have images that disappear once you stack them together.
And obviously, there's been a move towards federated learning. So rather than bringing all your data to centralized source, you can have data which can come together to be able to create the machine learning model. I think you can also define it as split learning. And I think you worked on inferring data from this split learning. Could you just outline the methods that you applied there?
Yes, this was a very interesting work we did a few years ago. I would say it's probably the first attack against federated learning. So we were looking at federated learning is basically a way to say we can train these models without giving them the actual raw data. What we could do is say we have a cloud provider that is connected to many devices, and each device will train their model, the local model, on local data. And instead of sending this data back to the main server, what they do is they send this some of the weights associated to the local model to the main model centrally. So this way, in federated learning, you can basically train a model on what they were saying is private data. So and the central model doesn't learn anything from local data. Well, that's what was the hope. But we noticed immediately that when you send this weights from these devices to the central model, well, the central model or the operator or the cloud provider would be able to infer actually something. I mean, you don't really protect the information because you can see how these weights evolve over time. But even worse, what we discovered is that if I'm, say, the owner of a phone and I'm training my local model, and you are also owner of a phone and you are training your model on your local data, what I can do, I can attack you and basically understand exactly what your local data is about by just looking at what you are sending to the central model. So it's not just the cloud provider that you have to be concerned about, because that is something that people consider kind of acceptable. I don't, but it's kind of accepted for some reason by customers that the cloud provider is trusted. But our message is that even if you trust the cloud provider, one of these components can be malicious, and this malicious component that is supposed to train on local data can actually attack another user that is training on his or her local data and learn about that specific training set. And so we use a very sophisticated technique called GAN, Generative Adversarial Networks, to basically be able to, over time, to regenerate exactly what the victim has on his phone or device. So that's pretty much what we did. And the same technique applies to split learning, as you mentioned before, because in split learning, people try to say, why don't we split the model in two? One half is on the device and is the one that is learning on raw data, and the other half is at the server. So the server doesn't see really raw data, but just sees the weights associated to the internal layers of the model. But again, the story is always the same, that even if you see weights coming up to you and you see how these weights evolve in the model, you will be able to learn anyway things about the training set. So the story is always the same. If you try to obscure things without using proper cryptographic techniques, or it's not going to work, right? But in the federated learning case, the uniqueness of that work was that even users that are supposed to be the victims sometimes, they could be the malicious party, and they can try to attack other users. So our paper was kind of a warning to the people that were investing in federated learning, is that we should consider also this kind of potential attacks, and not just the cloud provider per se.
Yeah. And obviously homomorphic encryption provides an opportunity to be able to train neural networks with encrypted data, and also we can use SVM methods to be able to process homomorphic encrypted data. So hopefully that will help a little bit in the future. So my penultimate question is that you worked on collusion resistance group signatures. Could you just explain what a group signature is, what its application is, and how you can stop this collusion?
Yes, that was a work I did when I was at the IBM in Switzerland, and I worked with researchers there. We came up with, so at that time, so first of all, what is a group signature? So imagine you want to sign a message and you use a digital signature. That's common technology. But now suppose you want to add some privacy. So you want to sign on behalf, say, of a university or a bank or an institution, and you don't want to reveal necessarily your identity. Of course, you can have a single key and a single public key for the bank or the institution, and everyone will share this secret signing key, and everybody will be able to sign. But you can imagine this is not a good solution, because you have a single signing key that is shared by multiple users. In group signature, instead, you allow users to have their own signing key, but they can still sign under a single public key, which is the public key of the institution. So you can sign on behalf of your university. So someone will see your message and say, oh, this is signed by your university, and it's a legitimate message, has not been tampered with, it's fine. But group signatures also allows you to add what is called accountability. So meaning, if you sign on behalf of the university, you can sign something that is, objectable or debatable or something that, or malicious. So how can we trace back to the actual signer if it's anonymous? Well, in group signature, you have a party. Sometimes could be the same as the entity itself, but usually is an external entity that has a key that can open a group signature and say, okay, I can reveal in case of dispute who the signer was. So group signature is a very interesting object and allows you anonymity, but at the same time accountability. And I think that should have more space, in my opinion, even in the blockchain scenario. But what we did at that time, this was many, many years ago. I think it was 2000, I believe, crypto 2000. At that time, there were no probably very efficient coalition-resistant signature schemes. It was first signature based on standard assumptions, first of all, and was resistant against attacks where, imagine there are attacks where these participants in the institutions or university, they put together their keys and they try to be undetectable. So they try to still be able to sign on behalf of the institution. But now in case of dispute, the person or the entity that is supposed to open the signature won't be able to do it. And there were schemes acceptable to this kind of attacks, and our scheme basically resolved that issue. That even if you try to collude with other users within the organization, you will not be able to sign anonymously, completely anonymously. But I think the biggest technique that we devised was mostly the efficiency. I think that the innovation of that paper was mostly on the efficiency side, because it was extremely efficient for at least for RSA kind of based schemes at that time.
Yeah. Yeah. And obviously it's extended into elliptic curves now, and hopefully it'll extend into lattice-based methods into the future for group signatures. So my last question is a kind of difficult one, but if you could change one thing about your career, what would it have been?
I will not change much, to be honest, because I'm proud. But maybe because I'm recognizing the importance of machine learning today, and I remember when I was a student, I took a class on neural networks and backpropagation at that time, and that was completely fascinating. I mean, if you think about it, the way we use computers now with LLM that help us doing everything, but even coding, I'm using a lot of help with coding and everything through LLM. I mean, if you think about it, this is how computers are supposed to work. You're not supposed to spend hours, programming or writing code. You should learn coding, of course, because that's important. It's like Latin. You should learn Latin, but you don't have to necessarily use it. But this is how computers are supposed to be, and this was my dream, like when I was a kid, and now it's happening. And I wish I had spent more time recognizing the importance of machine learning at that time. I think when I look at this, I was really intrigued by intelligent machines, neural networks, but then I focused more on the cryptography side. So maybe if I can change something, I would probably focus early on my research on machine learning, and always with combination with cryptography and security, because that's my true passion. But that's something I would change.
Yeah. I suppose if you draw a Venn diagram of AI and or Gen AI and cryptography, the bit in the middle is the real sweet spot. That's where we create trusted computing, trusted storage, and trusted digital identity, and so on. I think if we don't have that merger of the two, then we're in trouble. That it'll be the wild west of Gen AI.
Exactly.
So
You identified exactly the point. Think about it. Even this discussion we are having,
mm,
in the future, it could be completely fake. It could
yeah,
be my image could be completely
yeah,
fake. You could be
yeah,
completely synthetic, right? My voice
yeah,
could be synthetic. Everything could be synthetic. So the future is, how do we identify through humans, in general, or human products. And cryptography here plays a significant role. Anything that has to do with identification,
mm,
cryptography plays a significant role. So I think this is what excites me
yeah.
for the future, is definitely recognizing something real from synthetic, and cryptography here can be definitely the technology that will make the difference.
That's great. Well, Giuseppe, it's been a real privilege to speak with you today. I've taken up nearly an hour and a half of your time, but it's really great to talk about someone who's doing research into machine learning, Gen AI, and bridging that to cryptography. And I think keep up the great work, and it should be an exciting time ahead over the next decade in research. But thanks so much for all your great work. It's been a privilege to read all your papers and to hear your viewpoints on things. So thank you.
Thank you so much, Bill.